know our galaxy has objects called neutron stars that are just giant nuclei? And did you know that the amount of uranium fuel needed to run a large nuclear power plant for an entire year is so small that it could fit under your kitchen table? And did you know that doctors increasingly rely on nuclear medicine techniques, which go by friendly-sounding names such as PET scans or CAT scans or proton therapy? What is nuclear physics and where did it come from? During the 20th century, nuclear physics emerged from the shadow of chemistry to become much more than chemistry. For example, the sun is not a chemical fire. Lord Kelvin in the 19th century did not know about nuclear physics. This led him to wildly underestimate the age of the sun and of the earth.
खुद का बिजनेस स्टार्ट करना है, लेकिन इन्वेस्टमेंट नहीं करना. Yes, it is possible to start your own business with zero.
Estimate the age of the sun and of the earth. Lord Kelvin was wrong because, to everyone's surprise, the dream of medieval alchemists has been attained. One element can change into another. The sun changes hydrogen into helium. But it can't be done with chemistry. The philosopher's stone of the alchemists turns out to be the nucleus, involving forces much greater than anything in chemistry. A nucleus consists of protons and neutrons, and these protons and neutrons are held together by the strong nuclear force. That strong nuclear force is 100 times stronger than the electric force, which holds the positive nucleus and the negative electrons together in the atom. Nuclear physics studies how the energy changes when nuclei are combined and when they're taken apart. So let's look. Which are the easiest nuclei to combine or take apart? Iron, with 26 protons, is the hardest to take apart. It has the greatest binding energy. And so fission, when we split nuclei much larger than iron can release energy when they're split up. And fusion, combining nuclei much smaller than iron, release energy when they're fused together into a bigger nucleus. Hydrogen nuclei, which are the smallest, provide the most energy when they're combined. That's what happens in the sun. The biggest nuclei, like uranium, provide the most energy when they're split or fission. Either way, nuclei provide the most powerful source of energy in the universe through nuclear fission and nuclear fusion. Fission is the energy behind the nuclear bombs that were dropped on Hiroshima and Nagasaki, the hundreds of nuclear power plants worldwide providing electrical power, and the nuclear submarines, nuclear aircraft carriers, and nuclear icebreakers. Energy from fusion is harder for humans to harness. We can do it in hydrogen bombs, which use intense heat from fission bombs to fuse hydrogen into helium, making a thermonuclear weapon. Scientists are working on the dream of fusion-based nuclear power to provide clean, seemingly unlimited power by fusing isotopes of hydrogen into helium. But fusion is where the sun gets its energy for billions of years, from fusing hydrogen to helium and then later helium to carbon and oxygen. All of our energy, from solar power, wind power, hydroelectricity, coal, oil, natural gas, originally comes from hydrogen fusion in the sun. However, nuclear physics is far, far more than just a couple of controversial applications. Nuclear physics is about everything possible that can be done with the nucleus. For me, nuclear physics is much more about studying collisions of nuclei in experimental halls, like at the Thomas Jefferson National Accelerator Facility, where I do my research and where we seek to advance fundamental knowledge. Here in this first lecture, we're going to do a whirlwind tour of nuclear physics. But don't worry, we'll explore all of these topics again, step by step, later in the course. Now, the periodic table is great for organizing atoms. We just count the number of protons, we'll have the same number of electrons if it's a neutral atom, and then, well, hydrogen is basically 1 eum, helium is 2 eum, neon is 10 eum, uranium is 92 eum. But each element, and each element corresponds to a specific number of protons, has more than one possible nucleus. These isotopes, what physicists call nuclides, have a different number of neutrons. So if we look at carbon, carbon has 6 protons. Carbon-12 with 6 protons and 6 neutrons is the most common isotope. It's the most stable one. Carbon-14 still has 6 protons because it's carbon, but with 8 neutrons is famously unstable. But carbon has isotopes ranging from carbon-8 with only 2 neutrons